Okay, folks, we're continuing on our discussion of substitution techniques for first-order ODEs. We're now going to look at what are called homogeneous substitutions. Quick warning, this word homogeneous in math carries a lot of different meanings. And this is different than the meaning than when we said an equation was homogeneous if you could write it as dy dx plus p of x, y is equal to 0. So this is our definition of homogeneity that we gave in one sentence earlier on. That's different than this definition here. Okay? In the second definition, we're going to say that a homogeneous equation is going to be written in this form, where we have f of y over x. I'm not too worried about the classification here, but just know that this is one of the substitution techniques that we can try. So the key is if you can write it as some function of y over x, to use the substitution v equals y over x. Let's go ahead and try that here. So I can rewrite this as dy dx is equal to y over x plus the square root of x squared minus y squared all over x. And I've forgotten something. I want to specify that x has to be positive for this particular ODE. Why? Because what I'd like to do is I'd like to pass this x inside the square root. So I can go ahead and do so, and I can bring it in as x squared, but I can only do that leaving the sign alone if I know that x is already greater than 0. Okay. So then we get that dy dx is equal to y over x, and I dropped a sign there, plus the square root of 1 minus x over y quantity squared. So now we're ready to do this substitution. Now that we've written it as a function of y over x, we can try the substitution v equals y over x. So let's let v equal y over x. A consequence of that is that well, I don't want to do the quotient rule. Let's go ahead and set this up to do the product rule. So we'd say that y is equal to x times v, multiplying this x over to the other side. Now if we differentiate both sides with respect to x, we get that dy dx is equal to the first times the derivative of the second plus the second times the derivative of the first. Or that dy dx is equivalent to x dv dx plus v. So going ahead and making our substitutions right here, we're going to replace dy dx with x dy dx plus v. Oops, I'm sorry, x dv dx. Is equal to v plus 1, or plus the square root of 1 minus v squared. Notice in this case the v's cancel. So we get that dv dx is equal to the square root of 1 minus v squared divided by x. This is now a separable equation, which is fortunate, but that's the reason why we do that substitution. So we can now go ahead and treat these fractions as we usually do with separable equations. We get this expression here. Integrating both sides. On the left-hand side, do you remember what that is? What function when we took its derivative was 1 over the square root of 1 minus the variable squared. That was the arc sign. And that's equal to the natural log of the absolute value of x plus c. We assume, though, that x was positive, so we don't need to worry about those absolute values. Taking the sign of both sides, if we take the sign of both sides of this equation, we're going to get that v is equal to the sine of the natural log of x plus c. We're not done. Remember, this was just a substitution. We did the substitution in order to get it down to a separable equation. Originally, our substitution right here was that v is supposed to be y over x. So now we're going to back substitute. We said that v is y over x. So we get the y over x is equal to the sine, the natural log of x plus c, or finally that y of x is equal to x sine of the natural log of x plus c. We've now solved this differential equation by using the substitution v equals y over x.